Hi, welcome to my talk about data-oriented programming. It will be a slightly different talk than most of the other talks today for two reasons. First of all, I've had a huge cold for about a week now and haven't slept for 2 days, so that might come in here and there. And I actually won't show that much code. It's more of a conceptual talk, because that's the stuff I like, so that's the stuff I like to talk about. But before we talk about data-oriented programming, there's something I would like to discuss. Since there are quite a few paradigms out there, like object-oriented programming, functional programming, and topic of the day, data-oriented programming. And I always feel there's a bit of a conflict between the paradigms, where people who like one paradigm kind of hate the other paradigms. And I think this is a bit of a waste. Since functional or object-oriented programmers would say functional programming is like way too complicated way to solve a problem, the functional programmers are saying the object-oriented programmers, object-oriented programming has been dead for about 20 years. And I also get remarks at assignments that, oh yeah, we're not going to use immutability because that's functional programming, and we're doing object-oriented programming instead. And I don't really like this, because a lot of energy is spent basically hating other paradigms. Well, we could also use that energy to learn the other paradigms and become a better programmer. Because most paradigms are very good in solving a specific problem within a specific context. So by learning more paradigms, you actually become better at solving more and more problems. So Brian Getz, the Java language architect, actually has a really nice talk about this, OO versus FP pick 2. And he ended with this quote, where you shouldn't be a functional programmer, you don't be an object-oriented programmer, but be a better programmer. And I got quite inspired by this, and if there's anything you remember from my talk, I hope it's going to be this. Now let's actually start the talk. Hello everyone, my name is Ties van der Ven. I work for a company called JDriven. I did quite a bit of Java in my days, but last few years I mostly did Kotlin and even dipped a bit into Scala. I try to be a bit of a functional programming advocate, where I try to show that you actually don't need a whole mathematical background to do programming. Basically, most core concepts are quite simple. And what I really enjoy about software engineering are the underlying software engineering principles. That's the stuff that makes me happy. So when about half a year ago, Brian Getz wrote this article that data-oriented programming is coming to Java, I was quite interested, because I didn't know what data-oriented programming was. And the way it's introduced into Java is because of records, sealed classes, and pattern matching. But yeah, I figured Kotlin has had these for years now, so I might as well do this talk in Kotlin. And because the way I learn the best is by explaining it to others. So in a sense, you're all here because I wanted to learn something about data-oriented programming. So what will we talk about today? We're going to start with what is data-oriented programming. We're going to try to go a bit conceptual, a bit to the extreme, just to wrap our heads around what the actual concept is. We're going to go to a bit about why you should do data-oriented programming, what problems does it solve, and hopefully in the end I can show you a tiny bit of how to actually use data-oriented programming and how it compares to object-oriented programming. So a good thing to start with is comparing it to the other two paradigms, object-oriented programming and functional programming. So to remind yourself, what is object-oriented programming in about 30 seconds, so it won't be fully complete. But the whole idea here is that everything is an object. And it really embraces encapsulation to create boundaries among data, where you basically create a situation that you ask an object to do something for me. I don't care how you do it, as long as you do it for me. And it, of course, gives us access to inheritance. So within object-oriented programming, if we have a class, we actually don't really care about that data. We mostly care about what functionality does this class offer us. It may choose to expose the data with getters, but it doesn't have to. Because within object-oriented programming, we're more about do some logic, and I don't care what you need to do that logic, as long as you do it for me. So in functional programming, the whole idea is that everything is a function. So here, higher order functions are a big thing, which are functions that either return a function or receive function as an argument. And they use this to create very small, very abstract building blocks, and basically use composition to tie these building blocks together to create a bit of software. So what is data-oriented programming? Well, where in object-oriented programming, everything is about objects. In function programming, everything is about functions. In data-oriented programming, everything is about the data. And this sounds quite abstract, so let's see what this is. Well, in data-oriented programming, we still, if we have a type, we actually don't really care about that bit. We mostly care about the data that's inside. The person is just a bit of a wrapper. Now, why is this a thing? If you look at a lot of programs out there, basically all applications, or most applications, are just data streams. And within a data stream, you basically do data transformation. So let's visualize this a bit better. So a data stream is just, you have a source that emits data and a sink that receives data in the other end. And within data streams, you basically only have three kinds of operations. We have map operations, which transforms data into different data. We have filter operations, which removes data from the stream. And we have branching operations that basically divides it into multiple sinks. And if you take this very abstract approach to data stream, you can actually basically map most applications to just using these functions. To give a bit of an example, a standard CRUD application which retrieves data from a database, we can basically describe it like this, where we have a source, which is the user. Then we may want to do some security checking. Well, this is basically a filter operation because it may remove data from the stream. It may stop the stream from going any further. We then may want to do some input filtering, so make sure that the input is correct. Otherwise, we remove it from the stream. So again, this is a filter operation. Now we turn the user input into some sort of database query. This is a mapping operation. We transform data. Then we need to transform our query into an entity, and we may need some repository for that. And in the end, we map our entity to a response, and we then give that response to our sink, our user. So basically, a lot of applications can be written in terms of map and filter operations. And with the data-oriented programming approach, they basically think, well, if basically all we do is maps and filter operations, why should we even use types? Because types, if you declare a custom type, you don't have a map operation, you don't have a filter operation on it, you have to write those all yourself. Why not instead use generic data structures like maps and lists, where basically have huge amounts of collections of just methods to transform and filter data? To put a bit in perspective, for example, if you take JSON, it starts as a map. Most things will actually then turn it into a map. And then in order to turn it into a type, you actually need a library like Jackson or something, which does all kind of reflection magic to make that so. Within like real data-oriented programming way of thinking, they're like, why do that last step if you can just keep it a map and keep on using that map? So it's all about the data. It's not about the type. And types can get into the way of data transformation. So does it mean that I'm saying now, oh, we should completely stop using types? Well, in languages like Clojure, which is like a real data-oriented programming language, they actually don't really use types. It's considered a bit of an anti-pattern there. So, but because types make data transformation harder. On the other hand, I kind of love types myself because they introduce a lot of compile time safety and require a lot less testing. And in languages like Clojure, everything hands-on. There's a bit of things that simulate typing, and they basically rely on lots of testing to make sure everything works correct. But in languages like Kotlin and Java, for example, I would still say, let's use types. But the whole thinking in hash maps, that's basically just there to give you an example of what is actually data-oriented programming to the core. Now we understand that, we can see how we can apply those principles. So within Kotlin and the rest of the presentation, I just assume types instead of hash maps. So with types, thinking from a data-oriented programming perspective, it's not, again, really about the type. We may have a person there, but it's more about the primitives. And the type person is more of a specification. Basically, this is just a group of data. And these are, the name is of type int, of the age is of type int, and the name is of type string and such. So types are more about grouping data. So it's perfectly fine to basically break up the person type into a name and age type, or a username password type, or just use the primitives. Basically, it's all about the data. You don't have to be stuck to one object, a person object. Just feel free to tear it apart and use whatever you need, wherever you need it. This does come at that you need some prerequisites, because we're in object-oriented programming, we have this nice shell around our data, which protects the data to prevent it from going into an invalid state. Within data-oriented programming, we don't really care about the type. We don't have that protective data layer to protect our types. So we need to do input validation, and we need to make sure our data is valid. It also means you can't do data-oriented programming style without using immutability. Because if you're breaking up types like this, if person would be mutable, you get very, very weird situations on your application. So you don't want that. So if you want to do this approach, immutability is key. But if you do this, there are a few benefits you can get, especially in opposed to object-oriented programming. It's a bit in performance, a little bit in security, but mostly about dependency management. So performance, if your code hot paths, if you're always stuck to like a person object to represent your data, that might not be the most optimal way to represent your data to do a certain computation. Within data-oriented programming, we don't really care about the person object, we care about the data inside it. So it's perfectly fine with this within this paradigm to just take the data out of a person object and turn it into, for example, arrays or even arrays to do index-based lookups. Just use whatever representation of the data is best to solve your problem. Don't be stuck to just a person class that you have, and you have methods to act upon that person class. It can help in some cases with security. Because again, a person might have a username and a password. So every time you try to log or persist a person, you need to make sure you're not logging this sensitive information. If you're breaking up your data, you basically only supply the data that you absolutely need. So you're always working with the least amount of data needed to solve your problem, which automatically improves security in this sense. Although I must admit, this is a minor benefit. The big benefit comes from dependency management. Where in object-oriented programming, we combine state and functionality together. And in data-oriented programming, because we don't really care about the classes and they can basically change all the time, we basically have to separate those two. And that does have some advantages. For example, let's implement the save method on a person in an object-oriented way. In object-oriented way, we basically want to add that method to the person because we basically want to say, person, persist yourself, I don't care how. But in order to do the persistent, the person needs some sort of data access helper, transaction manager thing to do its work. And there are basically 3 ways to implement that. One of the things we can do is pass it along the constructor. But now we have the problem that to create a person, we now need to have all kinds of side effect methods that the person needs to perform all its use cases. So object creation became a lot harder now. We can of course cheat by doing the data access helper through a static lookup, but now we cannot mock the data access helper anymore. So we're basically left with the third way, where we can just pass it as an argument to our save method. But now we have the problem that we basically divided the logic of how to save, how to persist a person between the person and the component calling the person. So this is not really a very object-oriented approach. And all 3 have a big disadvantage. because now person is dependent on data access helper, which means person is dependent on all its side effects. For example, a data access helper and a REST template helper, which means all components that depend on person now also depend on all the dependencies of person. So you can get quite a complex dependency tree this way. Another thing is that although it doesn't necessarily scale that well if the amount of use cases grows. Because most applications, in my experience, don't get smaller over time. They usually just keep adding and adding on use cases. So in the beginning of your application, you may only have 2 use cases on person, but 2 years later, person can just grow and grow and grow and grow. And I've seen this happen, and I've seen classes with like hundreds of or thousands of lines of code just to accommodate all possible use cases. So the data-oriented approach is basically we can't mix, separate state, and we have to separate state and functionality. So we move the functionality away from the state and just pass the data, the state, as an argument to our component. And this basically looks like this, where a component does one use case. Well, for example, one uses a data access helper, and another component uses a REST helper to solve the problem. And now all the logic of our use case is within the component. And the person is just data. It's just passed along to the component. And when you see this, you may think, hey, that actually looks a bit familiar, because this is basically what you do in Spring Framework. So if you use Spring, then you're basically already doing quite a data-oriented programming approach, where if you think about it, you have Spring Beans, which don't really have state. They only have access to dependencies needed to solve the use cases. And you basically just pass the data to that component. So if you're using things like Spring Framework, you're already programming in a data-oriented style without maybe even realizing it. But this is basically the reason why Spring does it that way, because our dependency tree looks a lot cleaner that way. Because all the components are only dependent on the things that they need to operate. And while everything depends on person, person is just data. It doesn't depend on anything. Which also means that if you want to add a use case in the future, we just add one to the side of this. But most importantly, if you want to remove a use case, in object-oriented programming, are you really going to delete that one method on person? How are you sure it's not used anywhere in any code path anymore? With data-oriented programming, all the logic is within one component. So if you want to remove a component, just remove that and you're done. So adding the components and scaling down the components is actually much easier in a data-oriented programming way than in an object-oriented programming way. So should you now just stop adding functionality to code, to state? Well, not really. It's just that be a bit careful to what it does to your dependencies. Be a bit careful about how much business logic are you putting in the next to your state, because it can grow out of control. And most importantly, be pragmatic and don't be dogmatic. Just do whatever works for you, and just refactor if things could go better. We have a bit of time left, so we're going to talk about what patterns, object-oriented programming patterns, we can still do in a data-oriented programming way. Because object-oriented programming also gives us polymorphism, which is about sharing types, and it also makes sure we can employ the strategy pattern, which is my favorite object-oriented programming pattern. So what was the strategy pattern? We can create an interface credit card, which has a payment method. Now, you can create classes like MasterCard and Visa cards which implement this interface and implement the payment method. And now we have a doLogic function which takes a credit card as an argument, and it can take any credit card and just call the pay method on it. Which means if we ever add a new credit card, a third one, we just implement the interface and this function will work on that. And everything is compile time safe because that credit card needs to implement the credit card interface, or else we can't call the doLogic function. But the problem here is that we're now mixing data and state and functionality again, because we have a pay method that's part the credit of the MasterCard will have some state and also have a pay method. So how would we do this in the data-oriented programming way? In data-oriented programming, we still have an interface. We still have our classes that implement this interface, but we don't have any methods in the interface anymore. And this is where the power of pattern matching comes in, where if we get a credit card, we can now match on the credit card. And if it's a MasterCard, go into one direction, and if it's a Visa card, go into another direction. Unfortunately, with this construction, we still need an else statement, but because what if it's not one of those two? And this is where this is different for the object-oriented approach, where basically we get full compile time safety if we ever add another function, if we ever add another class. We don't have that right now. Luckily, Kotlin also supports sealed types, which means now the compiler knows that MasterCard and Visa card are the only two possible implementations. And now our when statement actually don't compile anymore if we add another statement, or if we add or remove one of the classes, then our code will no longer compile. So this allows us to basically do the strategy pattern, but in a fully data-oriented programming way. It does have a downside that it might cause you to basically re-implement the payment method a few times. But it doesn't always have to be a downside, because there's probably a reason why you have multiple use cases. So you probably want to have multiple different ways to implement the payment method, or they might be different through these use cases. So if you find yourself doing stuff like this, where you need to add Boolean flags to the pay method, or add multiple pay methods in your strategy pattern, then actually you're trying to to program multiple paths within one use case. And basically that's just bad code. So if you find yourself doing this, the data-oriented approach might be the best approach for you. So since we're kind of almost out of time, concluding, most applications basically do data transformation. So treating data as data basically encourages to think in the terms of data transformations. Dependencies of your application matter, so be a bit careful by mixing state and functionality. And above all, I've also shown you that we can still do object-oriented programming patterns within a data-oriented programming way. And I hope I inspired you a bit to actually look a bit into data-oriented programming, to try out the pattern matching and sealed classes. And basically want to end with a slightly adjusted quote, because Brian Getz didn't really know about data-oriented programming when he gave that talk yet. So I would like to end with, don't be a functional programmer, don't be an object-oriented programmer, don't be a data-oriented programmer, be a better programmer. So thank you so much for your attention, and enjoy the rest of the conference.